In this demonstration, a charged balloon is brought near an electroscope. An electroscope has its leaves move apart when a balloon is brought close. When the balloon is touched, it remains charged until my hand comes by and grounds it. Now let's break it down. In order to charge the balloon, we used a neutral cloth and balloon, rubbed them together so that it charged by friction, and then the charged balloon was brought near the neutral electroscope. It repelled the electrons to the leaves, making the electroscope polarized. The net negative charge on the bottom made the leaves spread apart. And finally, when the balloon is touched to the top, charges are transferred. This leaves the electroscope negatively charged until I touch it. That's the symbol for ground. Watch again. The leaves move apart when the balloon is brought close. Charges are transferred by conduction. This makes the electroscope remain negatively charged until I ground the electrons and they go away.
I used the negatively charged object to make the conduction paper float in this experiment.
The conduction paper started out neutral, meaning it had no charge, unlike the stick, which was negatively charged.
The conduction paper is charged by conduction and gets a negative charge.
The conduction stick and the conduction paper both have the same charge of negative, so they repel when the paper floats.
Why can a balloon rotate a heavy piece of wood?
Here we have a neutrally charged balloon and a neutrally charged rag, but when charging by friction, the electrons from the rag go to the balloon, causing the balloon to become negatively charged and leaving the rag to be positively charged.
This is the plank of wood before. It is neutral but polarized. As the balloon was negatively charged, it started to attract the positive end of the polarized wood. Because opposites attract, the negatively charged balloon causes the positive end of the polarized wood to turn.
In this experiment, we rubbed a cloth against the balloon to charge it and see if it would stick to the ceiling. The cloth rubs against the neutral balloon, causing friction to occur. Since the balloon was charged by friction, electrons were transferred and made the balloon's net charge become negative. Since the balloon is negatively charged, it repels the electrons on the ceiling, but since the ceiling is neutral, the protons attract the negative balloon, causing it to stick.
Before contact, both objects are neutrally charged.
Electrons from the hair get transferred to the comb through charging by friction.
Now that the hair is all the same positive charge, they repel each other, and since the comb is the opposite charge, it's attracted to it.
After the contact, all electrons from the hair are now in the comb, giving it a negative charge, and leaving only protons in the hair, giving it a positive charge. The charges of each object are now opposites.
Through charging by friction, the balloon becomes positively charged. This is caused by the rubbing together of the neutral cloth and the charged balloon. This allows for the transfer of electrons from the balloon to the cloth, making the balloon entirely positively charged.
Because the can is neutral, it will be attracted to the balloon once separation occurs between the protons and electrons. After the balloon becomes positively charged from charging by friction, it is left with only protons, giving it a positive charge. However, because the can is neutral, thereby having an equal number of protons and electrons, the can is polarized due to the separation of protons and electrons in the can, giving it a positively and negatively charged end. In this example, because the balloon is positively charged, the electrons in the can are attracted to it, causing the phenomenon in the video to occur.